Hello, calculus fans. Okay, so we want to determine where the local extrema and the inflection points of y equals natural log of x squared plus c are. And we're doing this as c moves. So we want to think of c as being a number that changes, and as it changes, what's going to happen to these local extrema and these inflection points? Now we're going to go ahead and assume that c is a positive number in everything that we're doing here. Well, if we're going to talk about local extrema and inflection points, then we need two derivatives. All right, the first derivative is 1 over x squared plus c times 2x. The 2x comes from the chain rule. Keep in mind that c is just a number. Now for a second derivative, we're going to need the quotient rule. So we do low d high minus high d low, square the bottom, and away we go. Again, keeping in mind in everything that we do here, c is just a number. Pretend it's a 3 or something like that. If we simplify the numerator, then we're going to get something that looks like this. We can combine the like terms now, so the 2x squared and the minus 4x squared can be combined. And then we get this. This will be our final expression that we're going to use for the second derivative. Okay, so let's think about local extrema now. So there's a critical number at x equals 0. Now notice that if we were to plug in a negative number, the derivative would be negative. If we plug a positive number in, the derivative would be positive. So we can use the first derivative test. That tells us there has to be a local minimum at x equals 0. Remember, if it's decreasing and then increasing, that tells you there's a local minimum. Now we could have actually used the second derivative test. Now let's go ahead and use that. Even though we've already used the first derivative test, this is a good use of the second derivative test. So if we plug in our critical number into the second derivative, then we're going to get this. Let's try to simplify this now. And we end up with 2c over c squared. Remember, we're assuming that c is a positive number, so this is itself going to be a positive number. All right, so the second derivative test tells us that the curve is concave up at x equals 0, and that makes x equals 0 a local minimum. So checking the concavity can classify critical points. Remember that it's possible that the second derivative test could be inconclusive. In this case, it was conclusive. All right, now let's check for possible points of inflection. So we'll set the second derivative equal to 0. We get 2c minus x squared is equal to 0. Essentially, we're just setting the numerator of the second derivative equal to 0. Now that's easy to solve for. We end up getting plus or minus square root of c if we try to solve this equation. You should check that out for yourself to make sure that you really do get plus or minus square root of c. Now that means square root of c and negative square root of c are possible points of inflection. The concavity might change there. Now if you pick numbers bigger than square root of c or less than negative square root of c, it's not hard to see that the second derivative is going to be negative. But if we pick values of x between negative square root of c and square root of c, the easiest thing to pick is x equals 0. If we were to plug x equals 0 back into the second derivative, we would see that we'd get a positive number. We had actually done that here. So that tells us that the concavity is changing at both of those points. At negative square root of c, it's changing from concave down to concave up, and then at positive square root of c, it changes from concave up to concave down. Now that makes both of those points inflection points. So we have two inflection points at negative square root of c and positive square root of c. So as you shift the value of c and you change what the graph looks like, you'll be able to get different graphs where the inflection point is going to move. Okay, that's all for now.